It's great to be back. I've been at KIPAC for some 6 years now, 5 years as a postdoc over the last year, so I've been split half-time between KIPAC and Copenhagen. So as you can see, I'm somewhat reluctant to leave. I like it here. And you can most probably find me here every winter at least. Okay, so I'm going to talk about cluster mass measurements. And if you're wondering why I'm going to talk about cluster masses in a dark energy session, and you didn't quite listen to all of Adam's talk, cluster cosmology is, I think, one of the most exciting probes that we have from the most recent years, and over the next decade, I think we're going to see very interesting results. And we've heard some of that from Adam. We're going to hear more from David and from Josh. And also what I would like to point out is that it's quite fashionable at KIPAC to be working in cluster cosmology. As our X-ray group that mainly worked with ROSAT so far, we have Eduardo, Ila, and Risa that publish cosmological constraints from an optical survey from SDSS. And then we have people working on SC cluster surveys as well with Brad and Nilima, who isn't here today. But also, it's very important, KIPAC is preparing for and is playing a leading role in many of the upcoming surveys. We're going to hear more about DES and LSST, but there's also involvement in some of the SPT works. And also, I think even the particle physicists have adopted a cluster as kind of their mascot for dark matter. So clearly clusters are a very nice thing. Okay, so cluster masses. Adam talked about how to recover cosmology from measuring the halo mass function. But what you have to keep in mind that when we do cluster surveys, when we find them in X-rays, SEs, or in the optical, we don't measure the cluster mass itself. We measure some observable that scales with the mass. And so we need to translate our observable to the actual cluster mass. And that is a translation that comes with some uncertainty. The halo mass function is quite steep. You can see there's many orders of magnitudes in terms of the number density of clusters. But on the x-axis on this plot, it's really just a bit more than 1 order of magnitude. So if you have a systematic uncertainty in the mass, you can shift your observables from the left to the right here, and that actually has quite a big influence on what the best recovered fit to the mass function is. What clusters measure best are sigma 8 and omega matter. Here's a plot from Eduardo's work. And so they measure constraints which are along this banana in sigma 8 omega matter space. And the nice thing is that this is roughly perpendicular to what the CMB measures. However, any uncertainty in cluster masses translates to a widening of the constraints in a direction that is roughly the same direction as these CMB contours. So that means that you lose a lot of the constraining power that you really want in order to complement CMB measurements. And already for the constraints that have been published today, sigma 8 and anything that's degenerate with it, the results are already limited by the systematic uncertainty in the mass normalization. And most published results assume the 10 to 15% systematic uncertainty. This is what Adam talked about just before the break, where in 2010 they marginalized over 15%. With our Weighing the Giants program, we reached 7% systematic uncertainty, but we still have to do better in order to not be just limited by this kind of annoying thing for DES and in particular for LSST. And I think this point was driven home to all of the cluster community very recently by the Planck results. So Planck reported a significant tension between the cosmology recovered from the SE cluster counts and the CMB cosmology. And they said that there's really 2 explanations for that. One is that they underestimate the mass bias that they have in their cluster measurements, or they actually detected neutrino masses at a fairly large mass, which is somewhat uncomfortable with the results that they get just from CMB and BAOs. But what they didn't take into account is that there are systematic uncertainties in the X-ray mass measurements that they use to calibrate their SD measurements. So, but if you were to add this uncertainty on top of their constraints, you can see this would widen exactly the constraints that they claim are in tension with the CMB. And so the tension would be significantly reduced. Okay, so how do we go about measuring clusters if we cannot use the X-ray telescopes because they're very hard to calibrate? What I do is weak lensing, and I think that is a very good method to measure cluster mass. It has many advantages. It measures the total mass. We don't need to rely on baryons as a tracer for what the total cluster mass is. And also, we don't really need to make any assumption on what the dynamical state of the cluster is. It's going to do lensing, no matter whether it's relaxed or whether it's merging. And in particular, looking forward to these upcoming optical surveys, it comes for free with any weak lensing survey, but of course it's not quite for free. You have to do a lot of work in order to get it right. And as with any cosmology, the key development really is that you need to control your systematic uncertainties. So this is what the Weighing the Giants program set out to do. We focused mainly on clusters that were selected from the Rose et al. Sky survey. This is the sample that Adam just talked about. So we have 50 of the most massive clusters in the universe, from redshift of 0.15 to about 0.7. For all of these, we collected nice Subaru imaging in at least 3 filters and some 5 filters, so we can use photosys. And it's particularly interesting because in terms of both the imaging depth and also the seeing, this is similar to LSST. And this is very much a KIPAC project. I call it everybody that's a KIPAC, and KIPAC blue and orange, and that's very colorful. So it's something that's very much at home here. I think many of you are now getting used to seeing these very wide field imaging. And yes, if you look at it from far away, it kind of looks empty. But if you look at it closer, there's lots of very nice galaxies. But what you need to keep in mind is also how this compares to those pretty images that you see from HST or from Chandra. So this is the baby bullet, or the cousin of the bullet cluster. Same thing, I like it a bit better. This is the HST image. In terms of our Subaru imaging, this is just a little piece in the middle. And the part that we actually care about for this cluster, the part where we measure, is between these 2 red circles. So how do you do cluster mass measurements? There's a number of ingredients that you need. Debbie's going to talk about more how to do cosmic shear. And, but for now, for the cluster, really what you need to care about is that lensing kind of aligns the ellipticities of galaxies tangentially to the cluster. So if you go to your cluster and you measure the average ellipticity of galaxies as a function of distance from the cluster center, you get a profile something like this. So first thing you need are shear measurements. Now to translate this to a mass, you need to make some kind of assumption on the mass distribution. An easy one is to simply fit a profile to that. But you need to choose which profile you want to fit. And then the normalization of the profile really gives you the mass of the cluster. But then there's a third component, which we so far haven't talked about as often, and that is you also need to know the redshifts of the galaxies in the cluster field, or at least you need to know the redshift distribution in that field. And so here we've taken one of our fields and we've bimped up galaxies by their redshift. This is the cluster redshift. So in front of the cluster, there's no shear on average. But behind the cluster, the shear depends on how far behind the cluster the galaxies are. So with these 3 components, it's very clear that this is also the 3 areas where systematics can come in and play a role. And so we need to understand just what the systematics of each of them are. And this is essentially the result of the first stage of weighing the giants. There's a lot of numbers here, but really it's these 3 parts that I introduced just before. All of these numbers are relatively small, even though we were conservative as well, but we don't really quite understand that, so let's make it 3% instead of 1%. But in the sum, we still do very, very well. Our total uncertainty in the end is 7%, which is roughly a factor of 2 improvement if you compare it with the 10 to 15% that you had to assume before. And a particularly nice thing, I think, is that there's also no principal roadblock for doing better, at least for clusters in the relatively local universe. We've had to look at this in particular. What I've been looking at is how to go from weighing the giants to the next steps, including up to LSST. And I'll mention a few of these things. But the nice thing is that the future improvements, they're relatively straightforward from a synergy with many of the efforts that are taking place on the cosmic shear side, as Debbie's going to talk about, but also the simulations, which Risa discussed on Wednesday. Okay, so these 3 points, I briefly spent 1 slide on each one of them. Again, cosmic shear is fully in Debbie's regime. I just put a picture up here. This is what we have to deal with. But what we're trying to infer is how much the shear changed this galaxy into looking like that. So that's kind of tricky. That's very difficult. And measuring shear unbiased is actually quite hard. Usually you end up biasing your shear low. And that would mean that you underestimate your cluster mass. And we already greatly profited from the cosmic shear community who set out and put out blind challenges for people to go and calibrate their shear estimators. So that worked very well already at this stage. As we go forward, there are a few things we have to keep in mind. Is that the shear in clusters is larger than for cosmic shear. We have to deal with something like 10% instead of 8% or so. It's a bit harder in the cluster fields because there's many more galaxies from the cluster, so we have to be quite good at correctly deblending them and correctly subtracting the backgrounds. On the plus side, we only need to calibrate shear to something like 1%. Remember, the goal is in the range of 2 to 5%. So if you can get the shear measurements unbiased to within 1%, we're doing well enough on that front. And so all of this we can do with additional image simulations, which we do have to at some point just do, but they are quite feasible. Now the second component is the mass model. And what lensing really does, as the photons travel from those background galaxies to us, they're going to be deflected by any mass along the line of sight. So what lensing measures is the projected mass along the line of sight. Now if we want to measure the halo mass function, we need to infer a three-dimensional mass, a spherical overdensity mass. Also, weak lensing is very noisy, and that means that typically, for most of the clusters, there are some exceptions which are very massive, where we can measure maybe more than one parameter, but usually even with these nice data sets, we can only measure one parameter reliably. So we do what any good astrophysicist does. We assume that clusters are spherical, and that allows it to kind of reduce the whole measurement to just one parameter. However, clusters are not quite spherical. They're very messy, and Risa, I think it's the color scale. I like the color scale. But it means that for this cluster, the mass that you recover actually depends on how you view it. If you view the cluster, which is quite triaxial, if you view it projected along line of sight, you're going to overestimate the mass. If you view it in the plane of the sky, you're going to underestimate the 3D mass. And that means that these 3D masses that you measure have an irreducible scatter that's of the order of 20%. The nice thing is, however, that if you average over a lot of clusters, these orientation biases basically average out. And so from simulations, you can show that the average mass is roughly unbiased. So the main path forward here is that we have to know these numbers a bit better. We have to know what's the density profile that we want to fit. Is it NFW or something else? What's the range that we should best fit it over? And there's a number of additional things for optical survey specifically. Okay, the third part then is the redshifts. So this is similar to the plot I showed before. These are the shear signals as a function of redshift for two clusters, one at redshift of 0.2, one at 0.5. And the grayscale here is the typical redshift distribution of galaxies down to limiting magnitude of 25. And you can see most galaxies live around 0.8. So for a cluster at 0.2, the shear signal is basically flat over that range. So if you get the redshift wrong, then that doesn't change your inferred mass very much. The inferred mass basically scales this line up and down. But if your cluster is at 0.5 and you get the redshift wrong, that actually makes a big difference in what you think the mass is. So because our sample is kind of the first one that really pushed to higher redshifts, we needed to implement photometric redshifts into our measurements. And one of the first things that we noticed is that you cannot just use the simple best fit redshift that your code gives you. You have to actually use the full redshift probability distribution. So that gives us a number of questions that we're going to have to address. How accurate do we need to measure the P of these? And how accurate can we actually measure them? And then it gets a bit more difficult because we have to do this in cluster fields where we know that there are more cluster galaxies, and we have to do it at fairly faint magnitudes. So I think in the three areas, this is going to be the hardest one to address. And now you expect me to show a plot of X-ray masses versus lensing masses. I'm still not going to show that, because I think one of the most important parts of our analysis was that we did it blindly. We had a very clear expectation. The clusters that we were using, they've been used in cosmology before, and we covered roughly the standard cosmology. So what we did not want is just to correct our masses until we get a result that we expected. And it's great that particle physicists, of course, are very used to this. This is an example from Aaron Rootman's review on the speed of light as a function of time. So there's clear shifts of paradigms, but people kind of just follow what they think they should measure. In our case, really what it meant is that we refrained from comparing to any other masses. That means that you need, in order then to test your masses, you need extensive testing, but that takes a lot of time, but also builds confidence that your results are reliable. So the first unblinding then that we did was to other weak lensing masses, and we actually found significant offsets of the order of 20%. So you can imagine if we had done this in an unblind fashion, then we would have been very tempted to look at our own masses and think about why they might be higher than other ones. But the way that we've done it, we're very confident that our masses are the better ones. Okay, but I can show you a little bit of a result, which is really part of what Adam just talked about, in that we have used these weak lensing masses now for the F-gas analysis. There are 12 clusters that are both in Rayleigh giants in the new F-gas sample. And so we could derive a mass calibration for at least these relaxed clusters. And what it changes between the analysis in 2008 and 2013, of course, the whole thing changed. Right? The weak lensing calibration is just one part. But it really does is to tighten the constraints in the omega matter direction. This is really where it helps. And this should be, in principle, straightforward to do even better in that we just need more clusters. And my time's up. So thanks to everyone for being KIPAC.
How did you resist the temptation to look at your masses for time?
That took a while. Yeah, we just did. There was so it's I have a plot of the lensing versus X-ray masses, and what I did was I multiplied all of the X-ray masses by a number, which was then hidden. And I don't know what the number is, so I have the plot, and so I know that there's a decent scaling. There's nothing that's obviously wrong, but the main result is the ratio of these two. And so that was a nice experiment to just say, okay, this is the number we don't want to measure, and this is a way to blind it. And it still gives you a way to kind of check up on your data, but the main result that you want to measure, you're insensitive to. And of course, it was quite exciting then to unblind. It's a nice exercise.